Uh, okay, thanks. So I'm talking about the evolution of disks and their formation. Again, pleasure to be here with all of you. Uh, I will give a brief history of star formation and disks. Basically, we've known for many decades that stars form within molecular clouds within our galaxy and indeed other galaxies. The molecular clouds can be tens of parsecs across in size, but embedded within them are dense cores, which can be typically a tenth of a parsec in size. And when you look carefully spectroscopically at the cores, you often see outflowing motions. We call them molecular outflows at speeds of tens of kilometers per second. So really the hierarchy is you go from clouds to cores. Cores have outflows. When you zoom in on the cores down to 100 AU scales, you see protostellar disks, and you also see jets emanating perpendicular to the disks. And then, of course, separately, we see extrasolar systems, which are the ultimate outcome of this process. Now, believe it or not, disks around stars were actually not actually observed until the 1990s. They were, of course, theorized based on the just the way that our solar system looks. But it was the Hubble Space Telescope in the 1990s that really took the first image of a disk here on the left that's seen in silhouette in the Orion Nebula, where there's so much ionizing radiation behind the disk that you see the disk as a dark oval due to absorption by the dust, and you can see the central star in optical. If you catch a different protostellar disk system edge-on, HST also revealed not only the disk structure illuminated by the star, but also which is seen to be changing over just a few year timescale. So there are clumps in the jets that are moving outward. Now that was the 1990s. Now the study of disks is being done primarily at millimeter and submillimeter wavelengths, and ALMA has revolutionized the field because for the nearest disks, it can essentially resolve AU scale. And what we've learned is that there is surprisingly, even very young disks have very clumpy structure, spiral arms, and even gaps, which can be interpreted to mean that there are planets that are embedded within the disk. So a lot seems to be happening in the disks at a very early time, within 1 million years or so of their birth. Now, a very important just physics point is that you don't actually expect to see a protostellar disk until you already have a protostar. That's the sequence. You can't have disk and then star because you can show with the back of the envelope calculation, as I've got on the slide here, that if you're following a Lagrangian fluid element and angular momentum is conserved, the specific angular momentum is conserved, so the centrifugal acceleration increases as 1 over r cubed as you follow a Lagrangian mass element, whereas the gravitational field, if it is primarily set by the central star mass, will, as you all know, increases 1 over r squared. And so since this quantity increases more rapidly as r decreases, you will eventually get to a point where the centrifugal effect balances gravity. And for nearly all mass shells, that standoff radius will be larger than the protostellar radius, and therefore you will form a disk. So nearly all the matter that ultimately goes into the star will have to first go into it, but that's a matter for another time, that prior to the central star formation, you cannot use this argument. And in fact, you cannot produce a centrifugal barrier in the prestellar phase, but that's a separate issue. Okay, I don't see my next slide, so I'm just waiting for it. Let me go back and forth. Okay, good. So as far as the jets and outflows that I mentioned earlier, it's been understood reasonably well through work by Masahiro Mashida and collaborators that you can understand both the outflow and the jet as separate entities that are launched by a magnetic field. If the magnetic field is primarily axis, then the magnetic effect can fling matter out at the edge of the so-called first hydrostatic core, which has a size of several astronomical units, and that creates the kind of moderate velocity outflow at tens of kilometers per second. Whereas once you form a central object of stellar dimensions, in that region, the twisted field, the B phi component, becomes so strong and develops such a strong gradient that it can launch 100 km per second jets. So this is something I'll come back to later in the talk. But basically, the ingredients you need are magnetic field, and you need ohmic resistivity, because a flux-frozen magnetic field with no resistivity actually would not even allow the formation of a disk. So you need the right balance of magnetic field and magnetic field dissipation to have the jets and the outflows. Okay, I'm going to come back to that slide, and I want to go ahead to this.
Shantanu,
yes.
Some of our audience have problem with network. Maybe it's better to stop your video. Then at the end, I will ask you to.
Okay, that's a good idea. I'll stop my video. Yeah. Okay. This plot is based on millimeter and submillimeter emission from disks in a paper by Jonathan Williams. And the interesting thing here is that, at least in this sample, the youngest disks that were identified are about 1 million years old, meaning the central protostar has been estimated to be 1 million years old. And the typical disk lifetime, you would say, is about 3 million years. And by 10 million years, they're almost all gone. That is, by the time the young stellar object is 10 million years old, the disks have been dissipated. So if you want to understand observationally, if you want to compare with observations, you really need to do long-term disk modeling, where you can model for at least a few million years of evolution. Currently, we cannot model. It's a problem of tremendous scale in time and space. So we cannot model the entire process the way ideally you might like in full 3 dimensions, with resolving large scale and small scale and integrating for a long, long time. You have to make some approximations. And the subject of this talk is the long-term disk evolution modeling that we've been doing. And to do that, you have to make some approximations in order to do the long-term evolution. So thin disk modeling is one way to do it. So you model the planar components in the disk, but you assume vertical hydrostatic equilibrium parallel to the rotation axis. You also do not resolve the central protostar, but you put in a sinc cell that can be several astronomical units in size. However, what you gain from this is the ability to do a self-consistent calculation of disk formation due to the collapse of the prestellar core. Prior to these kind of calculations, disk evolution calculations assumed some arbitrary initial state. In this case, you can start from the prestellar core itself, whose initial conditions are better constrained by observations, and follow the self-consistent collapse, disk formation, and then the disk evolution. And so we can evolve for million-year timescales using this approach. But because it is a thin disk model, you cannot model dynamical vertical motions like outflows, jet of the disk. So to accomplish this, we have a non-uniform grid in R and phi. Remember that the vertical motions are neglected, and you're assuming vertical hydrostatic equilibrium in that direction. And by having a logarithmically spaced grid in the radial direction, you can get the highest resolution in the region where you need it, where the protostar is forming and where the disk is also forming. Okay, I will move forward in the interest of time. That's just to give you a hint of how the numerical grid is set up for the finite differencing of the partial differential equations. This is a schematic of how the model works. The central region is really a sink. It's matter goes in but doesn't come out. But you can model the interior with stellar evolution models and assume you have a central star there and then estimate the stellar irradiation that would be coming out of the star. And that irradiation is taken into account in the model and contributes to heating of the disk. The disk is also heated by internal PDV compression, shocks, viscous heating if there is present. It also is cooling by radiating from its surface, but also being heated up by background irradiation, in addition to the stellar irradiation from the center. So these are some of the key features of the modeling. And in equation form, I will just go through quickly. I'm not going to spend time on this, but this is just for disclosure. You have your modeling surface density now because it's a thin disk approach. You have an equation of mass continuity, momentum equation, which has gas pressure and gravity terms, and you have an energy equation that has the PDV work term, and this somewhat more complicated term detailed here, which is essentially taking into account the cooling from the surface and the irradiated heat from the star and the background. So for those of you interested, we have a review paper on the entire scenario, which we've called the migrating embryo model. For reasons you will see, we generally in the early phase of the disk will form clumps. Those clumps can also be called embryos because many times or sometimes they lead to the development of companion stars, planets, or brown dwarfs. But those embryos don't stay still, they migrate. There's significant torques in these disks, especially at early times. So here's some of the main takeaway points about the early evolution of disks. You can expect significant gravitational instabilities in the disk. The disk is still accreting matter from the surrounding collapsing core, and that drives gravitational instabilities, which lead to the clumps. The clumps quickly start migrating. They can actually fall all the way into the central object, but they can be scattered, ejected. Sometimes they can come into a stable orbit, which I will show. But it's a rather chaotic evolution in that early phase. Okay, so this has some of the key results of this kind of modeling. Remember, the idea is it's self-consistent modeling from prestellar core collapse. If you start counting the mass accretion rate onto the central object after it's formed, then you see that there's an initial smooth phase of accretion, but then you go into this very bursty, flickering mode of accretion. We call that the early smooth phase, actually rather artificial because we have a finite sinc cell of a few astronomical units in the model. In reality, the stellar surface is much, much smaller, and the disk would actually form at an earlier time if you were resolving the center. But I'll come back to the smooth mode a bit later. Essentially, once a centrifugally supported disk is formed, the mean accretion rate, the background accretion rate drops significantly. But you get these periodic, actually I should say episodic bursts of accretion, which can go much, much higher than the background value. And those bursts of accretion are associated with the formation of clumps, which then migrate inward and go into the center. So the arrival of a clump at the center is one of the bursts, but there are times between these phases when the disk looks more like this. It's a quiescent disk, which does not have any clumps. But then the clumps form again, and they move in, and they create the next burst. This will generally go on as long, these frequent bursts will go on as long as there is significant matter falling onto the disk from the external medium. So we can understand the formation of these clumps through the so-called Toomre Q parameter, named after Alar Toomre, who developed the linear theory of stability of rotating disks. And so the very interesting point is that this Q parameter, which is a dimensionless number that comes out of linear theory, which tells you that if Q is less than 1, the disk becomes unstable. And you can see why Q would need to be small for instability, because the terms associated with gravity is large, or gravitational constant gets large in case you could tune that, which you can't, of course, but the gravity terms are in the denominator, and the terms that oppose gravity are in the numerator. This is the sound speed, which is associated with thermal pressure, and the rotation rate locally. So the linear analysis says Q is less than 1 leads to instability, and that's indeed what the nonlinear simulations show. You get self-gravitating clumps emerging in the disk when Q is less than 1. However, the nonlinear simulations also reveal that if Q is, say, of order 2 or slightly larger, even though the disk is stable, you do get persistent low amplitude non-axisymmetric perturbations. And that's another long story, which I won't go into. But there's always some persistent perturbations, or oscillations, I should say. And then there's an intermediate regime where Q is almost unstable according to the linear criterion, but you still get significant non-axisymmetric structure. So think of this as spiral arms, and think of this as spiral arms that have embedded clump. Another way of looking at the accretion rate, this is for another model where the accretion rate is now plotted on a linear scale, not logarithmic. And this allows us to see some other features. Again, before the disk forms here. Before that, you have a smooth accretion, which is understood theoretically to be more or less the isothermal sound speed cubed divided by the gravitational constant. That comes from self-similar collapse theory developed by Frank Xu in the 1970s, and the simulations more or less fit that, although the constant in front may be as large as 10. What you see here is if you plot the accretion rate and the average Toomre parameter of the disk in red, that the Toomre parameter after a burst goes down. The Toomre parameter is steadily decreasing as matter accumulates in the disk. Then when a clump or clumps fall to the center, the Toomre parameter goes up, the disk becomes stable again. And then as more matter accretes, it starts going down, down, down until you get to a Toomre parameter of order 1, and then you get a burst. And the bursts sometimes are small, sometimes they're large. But this is the basic mechanism. The mass accretion drives Q into instability episodically. And those episodes are more frequent early on when the mass loading of the disk is occurring at a high rate. And later, when the mass loading is occurring at a low rate, there's longer times between bursts. But this is not exactly predictable in a periodic way. Oops. Okay. All right, so why do the clumps move inward? Well, very simply, if you have a clump that's embedded within a spiral arm, the gravity of the spiral arm itself will exert torques on the clump. The leading part of the spiral is actually rotating faster than the clump and will pull the clump in forward, which will actually create a torque that drives the clump. It's like spinning an object, and then you try and spin it faster. It's going to tend to move outward. However, the trailing part of the arm does the opposite. It slows down the clump, which makes it spiral inward. And typically, you will have more mass in the outer part of the arm than the inner. And so the outer arm usually wins and creates a net negative torque that drives the clump inward. So now some simulations, sequence of images. This is a long-term evolution from 0.03 million years after the protostar forms to 4.5 million years. And in this simulation, and remember that more or less every simulation is a little bit different. Even though you're evolving deterministic equations, if you put slightly different perturbations into each model, even with the same parameters, you may get a different outcome in the end as far as clump formation. Or you can vary the parameters of the mass and angular momentum, and again, you get different outcomes. So there's a lot of sensitivity to the initial parameters or perturbations. And so you can run, if you run many realizations, you will see that in some cases, you form the clumps, and most of them do fall into the center. But eventually, one clump can become dominant and large enough that it can carve out a gap in the disk. And if it is successful in carving out a gap, it can actually settle into a stable orbit. So in this simulation, in the first million years, the radial position of this particular clump is moving around a lot as it is interacting with other clumps and being scattered. But eventually it's the only clump, and it settles, it creates a gap, and it settles into this 50 astronomical unit orbit. And it has a mass of about 5 Jupiter masses with a surrounding mini disk that contains another 5 Jupiter masses. So this mechanism may explain, in principle, binary star formation, but also, as in this case, the direct gravitational instability could explain the formation of wide orbit exoplanets and brown dwarfs. There are many observations now of exoplanets that orbit at tens or even over 100 astronomical units from the central star, and the standard core accretion model has a hard time explaining their existence. So it seems there is a role for gravitational instability to create at least some of the high mass gas giant planets that are seen at large distances from their host star. Another effect that you can get is during this phase when you may have multiple clumps, you can get a gaseous counterpart of the 3-body problem or 4 or 5-body problem. But essentially, you know that as soon as you have even 3 bodies, there's a significant chance that one body could be ejected from the system. Since these are gaseous clumps, they can't have such a close impact parameter with each other, so the probability is less than if you had 3 point masses. But nevertheless, sometimes clumps can be ejected, as in this model. This object is on its way out of the system. Its speed is larger than the escape speed due to the gravity of the other objects. And this object also has a kind of giant planet brown dwarf type mass. So the idea is that the free-floating brown dwarfs or giant planets that are seen in stellar clusters may be attributed to this kind of ejection mechanism rather than having formed in place through direct collapse. So these are really there's really 3 mechanisms at play in star and planet formation, at least that we know of, or that we think happen. One is, of course, the direct collapse of a molecular cloud core to form a star. This is traditional idea of star formation. Dense cores collapse to form stars, and then you form a disk, which may form planets. And those planets would form by the core accretion process, the accumulation of planetesimals. But the work I'm showing here is also really exploring this mechanism, which is that even if you have direct collapse, you form a disk, and the disk can then have gravitational instability, which can form an object which could be in the stellar mass domain. It could even be in the upper end of the planetary mass domain. And there's a lot of arguments among astronomers as to what is the definition of brown dwarf, especially. And so I think this is probably from a theorist physics point of view, the most clear way of thinking about it. Planets, no nuclear fusion. Brown dwarf, yes, you do have nuclear fusion. That's what distinguishes it from a planet, but never enough to reach the main sequence, which then would be the definition of a star. Okay, so I think I'm doing okay for time because I just have a few slides left. So I've been showing a lot of this long-term disk evolution with the models that are using the thin disk approximation. And thereby some of the things we're missing are the magnetic effects that create the vertical structure, the jets, the outflows. So the gold standard in this field ultimately would be to do long-term evolution that also was fully three-dimensional, included the magnetic field, but you can't just include magnetic field unless you include the non-ideal magnetohydrodynamics, because flux frozen magnetic field will lead to the so-called magnetic braking catastrophe where a disk doesn't even form, and we know that's not what nature does. So you need to dissipate the magnetic field in the inner regions to form a disk, but of course not so much that you wouldn't form a jet and outflow. So there's a lot of very interesting physics to be explored. I showed you results earlier that use the central sync cell, but in principle, you want to run models that can resolve all the way down to the central protostellar object. Okay, so I'm going to show you some work that we published with Masahiro Mashida last year. This is a 3D model using a nested grid approach. It's Cartesian nested grid. You have grids within grids. The coarsest outer grid is the size of a prestellar core, and the finest grid actually resolves down to about a solar radius. So it can actually resolve the central protostellar object, although not its interior structure. Now we, yeah, I'm almost done. We see.
So we have almost 5 minutes.
Okay, thank you. Okay, so in this simulation, as I said, with the long-term modeling, you can do millions of years of evolution and get to the phase that is usually observed. In the early phase, it's hard to catch the objects at a young age. There's not as many of them, and they're often embedded in a gaseous envelope, so they're harder to observe. In this 3D model, we're resolving the central protostar, 3D magnetic field and magnetic dissipation. The drawback is you can only evolve to, although this is further than has been done before, the previous results of this type were just evolving to just a few years after protostellar formation. So now you can integrate up to 2,000 years. Now remember that in this simulation, the simulation already ran for 100,000 years or so of evolution just to form the central star and disk. But then you can only go another 2,000 more years. So that's what I mean. As you probably know, in numerical simulations, as the physics makes the system evolve more quickly, the computer actually calculates more slowly. It's the inverse, because you're getting to high density structures where you need small grid size. Small grid size means you have to take a smaller time step according to the Courant criterion. And so the computer takes more and more time. So in this simulation, after 2,000 years, you've got this very strongly, if you look at, this is essentially the edge of the first hydrostatic core. The disk is within this region, and the field is wrapped around, but also has significant vertical and radial components, and matter's being flung out in these outflows. This is a density map. And deeper inside, a central protostellar object is formed, and a jet is being launched in that perpendicular to the disk, and there are knots in the jet, similar to what's observed. So here you've got 100 kilometer per second outflow, or jet. Here you've got tens of kilometer per second outflow, and here is the density of the protostellar disk. And this is kind of the inflowing matter onto the disk. So we can only comment on this early evolution while resolving the central object and having the magnetic field. And if we look at the mass accretion rate into the center in black, and in blue, the outflow mass, the mass outflowing, and the dark thicker lines are time averaged values, and the actual values are in thin line, and you can see there's a lot of flickering of the accretion rate. The accretion is not axisymmetric. It goes up and down, but these are not huge variations. These are not necessarily more than an order of magnitude, or they're less than order of magnitude fluctuations. And so we are seeing fluctuating flickering accretion rate, but not yet at this time the major gravitationally induced bursts, which can be orders of magnitude increase. Those would presumably happen at a later time if we could integrate far enough. But it's a very important future work to really link the long-term evolution that's been done without the magnetic field with the magnetic field modeling that right now is going to the early phase. Interestingly, if we look at the actual mass of the protostar in black versus time for these 2,000 years, and the mass of the disk, they intersect after about just over 1,000 years. The more natural state is that the disk mass becomes less than the protostellar mass, because if it was more massive, there would be significant Toomre instability, and you would draw matter into the center as a result. But there is this very brief early period where the disk can be more massive than the protostar. But after this time, for the next millions of years, as we've seen with the other calculations, the protostar mass remains larger than the disk mass. So there's always efficient accretion to the center. Interestingly, we find that the outflow mass is larger than the central protostellar mass or the disk mass. And you can see that in the accretion rate here too. So it's an interesting result that the outflows seem to carry away about 2/3 of the mass that is trying to form the star. Okay, so that's it. This is my summary, and I just want to say that the overall scenario is for the first few 100,000 years, you have gravitationally dominated phase with clumps and spiral arms, and this is where you can form companions, whether they're stars, brown dwarfs, or wide orbit gas giant planets. And the magnetic field adds another richness, which has been explored in many papers that I've referred to, but now the focus is on trying to do the full problem where you resolve the central protostar. And there's a lot more to be done in coming years. Thank you very much for listening. I'm done and can take questions.
Thanks for your interesting talk. We may have time to have some couple of questions. Please turn on your video. Okay.
Yes.
If any question, you may raise your hand. There is a question by Hussein Shanavar.
Yes. Okay, I see that. Yes. Yeah, it's very, thank you for the question. It's a very interesting phenomenon about the Q parameter, how, yes, if you go less than 1, vigorous instability, but then there's these other states where you're above the instability criterion, but you still get meaningful structure. That is really a theoretical result. It's been, people have been working on this, even in the context of spiral arms in galaxies, using stellar dynamics, since the 60s and 70s. But it's very hard to actually observe it because it's such a fine balance. This idea that when you're in the marginal state, the idea is that your disk can survive in the marginal state for a long time, and you have all this meaningful structure. I think it's a good question, but frankly, at this point, I don't know if it can be tested observationally, because when you try to estimate the Q parameter observationally, there's so many uncertainties of order unity, you can't exactly pin it down to saying, well, it's exactly 1.5, for example. So at this point, it's a theoretical idea, but it's used to explain why we do see so much structure, even in disks where you may not expect there to be a lot of external perturbations.
Okay, any other question? I have one question. You used gravitational instability as a source of viscosity, or you may use the standard alpha viscosity model?
Mm-hmm. Yeah, actually, most of our models have a bit of the standard alpha viscosity in there, so that at late times you still have some accretion going on after the gravitationally dominated phase has ended. But in the first few 100,000 years, the gravitational torque dominates.
Okay. There is another question by Muhammad Hosseini Rad. What would be the effect of non-ideal MHD on your results?
I think the non-ideal MHD, it is in the last slides I showed, does contain the non-ideal MHD of ohmic resistivity. However, it does not contain ambipolar diffusion or the Hall term, the two other main non-ideal MHD effects. Most generally, yes, you have to have the non-ideal MHD in order to allow the disk to form. Otherwise, the magnetic torques would be too strong and all matter would fall to the center. So it's needed under a full interplay of all three non-ideal MHD effects on the disk formation and evolution. I think that in some sense, probably nature has found some self-regulated state where there's just enough non-ideal MHD, you dissipate enough magnetic flux to form the disk. If you don't include magnetic, even these three, in other words, nature will find a way, right? And so even if you, for example, didn't include any of these non-ideal MHD results, then you would drag so much flux into the center. At some point, probably the field would reconnect, even due to any residual ohmic resistivity. So it's a complex field, and there's a lot more to be done. So I hope I answer your question sufficiently.
I have one more question. Is there any correlation between the embedded cloud with the accretion rate of the protoplanetary disk? I mean that there is any direct correlation between the properties of the cloud and the protostellar disk?
You mean the clump and the protostellar disk?
Yeah, yeah.
Mm-hmm. I think that you need sufficient mass in the protostellar disk to form the clump. The clump is usually there are about 10 Jupiter masses, and that you can understand in that they're the same as the first hydrostatic cores that form in the center of the collapse. 10 Jupiter masses is roughly where the internal kind of halt the collapse and have a kind of a self kind of a clump that maintains some integrity. So you need to accumulate at least 10 Jupiter masses in the so I think there is some correlation with how massive the disk is, certainly, and whether it can form clumps.
Okay, Dr. Sheikh Nizami, since you have a question, please ask your question.
Hello, thank you for your interesting talk. Just a second. Okay, so could you hear me?
Yes.
Okay, so the question I have is about, so as I saw in your talk, at the beginning you have studied the disk evolution totally via hydrodynamic simulation, and later you had a magnetic field and also outflow. I'm interested in knowing which of these agents, I mean hydrodynamic instabilities or outflow, are more efficient to drive accretion and remove angular momentum from the disk. During your study, which of these you found?
Yeah, it's a very good question. I think what we found with the hydrodynamic studies is that the gravitational torques are actually quite efficient at driving matter into rather small radii, certainly within a few astronomical units of the central star. Now, once it gets there, in that region, the temperature can be quite high. It can be irradiated by the central star, and the Toomre parameter can be well above 1. And so for that last bit of accretion actually onto the central star, I think that's where the magnetic effects are needed and have to become important. You just have a central sink cell, so you can avoid that issue. But in the full situation and in the 3D model that resolves the center, ultimately it is the magnetic field through outflow, magnetic braking, and jets that, or even magnetorotational instability, which can happen at an even later stage. These are the mechanisms by which you can do that final bit of accretion. Another way to think of it is gravitational instability is very good at reducing the disk mass to be a few tenths of the stellar mass. So a lot of the mass accumulation to the center is driven by gravitational instability. But if you want to get to a situation where the disk is only 1% of the central star mass, as you see in millimeter observations or the hypothetical minimum mass solar nebula, then you need additional mechanisms, which again, I think are primarily magnetic.
Okay, thanks again. Thanks again, Shantanu, for interesting talks. Thank you so much.
All right, thank you very much. It's been a pleasure to join you all. Thank you for listening.